Yeah, so first I'll very briefly motivate why we use ADS-CFT for thermalization of the quark gluon plasma, and then the biggest part will be about these gravitational shock waves I did in my first reference, and then in the last part I'll give put some advertisement for this latest paper where we also put the spectra, and hope you stay interested till the end because of the spectra. So the first question as a motivation is if we are cheating by using NS4 super young males, and well, the obvious answer is that we do. But on the other hand, I mean, if you look like we are comparing an SUN theory of n is infinite with 3 colors in QCD, but if you then look, for instance, at lattice results, you see that, well, they plot SU3, SU4, SU5, SU6, and you see they're all nicely on one line. So approximating 3 colors with infinite colors might not be so bad. The second question is we're using a supersymmetric theory, but on the other hand, if you put on some temperature, then supersymmetry is suppressed. So at least for thermal states, this might be fine. Well, you don't really know if it's also for thermalization, but similar, hopefully. Then, yeah, we don't have quarks, of course, but then most of the dynamics is dominated by gluons, because there are many more gluons than quarks. So we just basically replace the quarks by gluons if you look at if you fix the total energy density. And then, yeah, maybe the worst thing is that we're modeling things at infinite coupling, whereas you know that QCD is asymptotically free, so at high energies the coupling goes to 0. But on the other hand, I mean, you also know that the beta function, that this coupling only runs logarithmically, so perhaps at our energies we're not really in the weak coupling regime yet, and it's still strongly coupled. But then, yeah, there's also room for improvements, as you can see. But yeah, and one of my favorite pictures to show is why this all might make sense is these real pictures of a real. So you trap some fermions in some kind of narrow region, and then you let it go, and you see it expand. And these are fermions at unitarity, so they're very cold, and they behave like a strongly coupled fluid. And you can extract the viscosity of this thing, and it's quite close to 1/4 pi. It's somewhat bigger. And then you look at the quark gluon plasma, which is the hottest liquid basically produced. And you see that, of course, also this viscosity is 1/4 pi, which is computed by using ADS-CFT. So you see the hottest and the coldest fluid kind of are behaving very similarly. So you might think that all this, yeah, that by approximating everything with this NS4 stopping your meals, you're not doing so badly. This is the hope. So how do we do this in practice? So we follow basically this famous example by Chesler and Jaffe, where they collide these infinitely big shock waves. So they're infinitely big in the transverse plane, so the symmetry makes it much simpler. And so how is this defined? Well, you have some energy density at the incoming part. Maybe I should get this stick. And yeah, it's basically a Gaussian, and there are 2 parameters. So the one parameter is the width, and the second parameter is the energy density. Well, here in a formal field theory, so only the combination actually matters. You can make a dimensionless ratio. And what they find is you collide these 2 shocks, and you find some maximum a little bit higher than the sum of these 2. And then basically everything from here on is described by hydrodynamics, and it thermalizes very fast, and you have some expanding plasma. So so we follow this, and we only use gravity. So this is only solving Einstein equations. You could add other forces, of course, and it would make it more interesting. But I also want to know that if you go to very, very high energies, the energy grows, so gravity kind of dominates at very high energies. So this is the first thing to do, at least. So what do we find? So we did the same thing, but the only thing we changed was this width, actually. So this is the original example, and then this is an example where the width is twice, in our units at least, the width of these original shocks. And what you see is already quite interesting. So these shocks, they come together, and this peak is actually 3 times the original size. So what you really see is these shocks, they come in, they collide, and hydrodynamics is already describing this really quite well at this peak. And then you have some energy that's kind of stopped. So hydrodynamics applies, there's no velocity because the momentum has added up to 0. And then it explodes. Yeah, you have so much energy in the middle that it explodes hydrodynamically, and this is kind of what you see. But it's already quite interesting. But then you make the width smaller, so that's what we did over here, and this might be even more interesting because it's kind of what we say a new regime. And by the way, I put in here in the paper you won't find any units, but I fitted here. I fixed my units such that the total energy of the colliding shocks matches LHC units to get some intuition what comes out. But what you see is quite interesting because these shocks, if they're really narrow, they don't basically have time to thermalize. They just pass through. They do decay in the end, but initially they just pass through. and then the plasma only forms in the middle. And you see, if you look at this inset, I'll show it later on a bit more clearly, that first you have, of course, a peak because of the collision, but then there's a minimum, and then it starts, the plasma grows again later on, and that is still considerable energy, but it's only later on. And you even find some negative energy density over there.
So the peak there is twice the height?
This is almost, yeah, this is within numerical errors, exactly twice the height.
How you get from non-interact, like in linear order?
Yeah, this is just a linear superposition of these two waves, so I'll get to that, yes. So for the first part, I wanted to explain a little bit of heavy ion physics, which is already known since 1953, at least by the Russians. So this is the lambda model, and this lambda model is kind of approximating these two heavy ions. And yeah, it's rather crude. You just say they come together, they collide. When they overlap, they're fully thermalized by some, perhaps by a miracle. It is an assumption. And then, if you just assume this, you could solve this using some approximations, or you could solve the full evolution analytically and get out the spectra. So this is kind of interesting, and people got really interested in this, at least part of the community. The other part didn't believe that this was possible at all, so they were not interested. So this is at RIC. This actually matches quite well. So this is the lambda model. As a function of rapidity, the number of particles you find out as a result, and you fit the data really well. So and it's a very simple model, so there's not too much tweaking. So to me, it's very impressive. But then, of course, they made predictions for LHC, and this failed miserably. So yeah, it's a bit of a sad story. Here is the data of the LHC, and this green line, lambda 1, it's not really easy to see, but it's this line, and it's really much. The data is much wider. So then this lambda model, at least after LHC, is kind of dismissed. But for us, of course, it's very interesting, because if you look back to these shocks, and here this is kind of this lambda model, of course, these fixed shocks, because they overlap. It's described by hydrodynamics and it kind of explodes, so it's kind of very similar. But then we say if it goes to even higher energy, by Lorentz contraction, they get even narrower, and we find totally different dynamics, with also, of course, very different velocity fields, energy density fields in the middle. So yeah, for us it's very, at least curious. So this is what we call in the paper a dynamical crossover. So it's very low energy. You have this stopping, this piling up of energy. You can get a lot of, this maximum is much higher than the initial shocks. And then this explosion by hydro. Well, this is actually what I call a compressed lambda model, because lambda just assumed that if you have these two nuclei overlapping, that they thermalize at that point. But in our case, actually, we find the total energy is even higher than the sum of the two, because they compress during the collision. But if you plug in the numbers, then, well, maybe by a real miracle, that by RIC energy, we find precisely this lambda model without this compression. So this is kind of the intermediate regime, which is also very similar to the original shocks by Tresson and Javan. And then at high energy, it's also the interesting regime perhaps for high energy. You find more like this. The shocks come in, and there's no real stopping. So this stopping is kind of this hydrodynamics and expansion. Plasma forms in the middle, and this is actually the regime where hydrodynamics applies. So it applies in the plasma, but not in the shocks. And there's some negative energy density. Yeah, it's kind of weird perhaps, but it's very far from equilibrium, and it goes away later on. So it's not really a problem. Well, then another interesting thing to look at perhaps is the anisotropy, so the pressures. So I just showed the energy density. So you can also plot, of course, the pressures. So this is at the center of the narrow shock collision. And you see first the energy density and the longitudinal pressure goes up by a large amount because of the collision. But then it goes down, goes to a minimum, and then the energy density increases again. But the longitudinal pressure in red gets really negative. And yeah, here we plot the pressure over the energy density, and you see that the longitudinal pressure divided by the energy density goes all the way to -3. And at least for heavy ion physics, this was not really expected, because if you look at the boost invariant expanding plasma, then these kind of stress tensors apply, and you have like the energy density, and the longitudinal pressure is always minus the energy density. Well, because at small times, at least this term is kind of 0. But then because we start out with a collision where this energy density is almost 0, this term is actually kind of dominant over this term, and we find it -3 because we start with an energy density after the collision which is almost 0 and then grows again. So this is kind of a curious thing, and gives, of course, a very anisotropic, far from equilibrium behavior. So that's perhaps a lesson. And yeah, after that, hydrodynamics applies more or less over here. So just when the longitudinal pressure gets positive, hydrodynamics starts to apply. And then the last thing we really studied in these shocks is the question of boost invariance, which is also very interesting from a FEI point of view, because they kind of had the idea, and they saw it also in the data, that if you have these colliding nuclei, that at higher and higher energies, when the shocks would get narrower and narrower, things would get more and more boost invariant. So here I plot the energy density divided by the energy density at mid rapidity, so this is rapidity. So if it would be boost invariant, it would be totally flat, because it would be constant as a function of rapidity. Well, we see by this very wide shocks, well, it's not boost invariant at all. You see that it is well, it's more Gaussian and only like 0.6 units of the rapidity, and it goes down already by 30%. At these narrow shocks, it's slightly more boost invariant, so you still have this Gaussian, and it has width 2, but it's also not boost invariant. And more importantly, it doesn't get more and more boost invariant if you go to higher and higher energies. So in the end, so the initial state is not really boost invariant, which doesn't, of course, say that the final particles you find after the expansion by hydro will not become flatter, which they kind of find in the data later on. And then the question is, of course, if you understand why this all happens, and at least from the ADS point of view, we do understand this a little bit. I made some movies where you can follow these shocks in the bulk, and these are for these narrow shocks. So here you have these shocks coming in, they're kind of narrow, but yeah, in these Eddington-Finkelstein coordinates we use, they start colliding earlier in the bulk, and they're also broader, so that's kind of a funny coordinate thing, but that might not be very important. But what you see in the movie, so you see them colliding, and you really see the horizon here forming and a blob kind of hitting the boundary. And what we kind of say is that the collision is really non-linear near the horizon. Near the boundary, everything is approximately ADS, because it's that's your boundary condition, and the rest is always a non-normalizable mode. So here everything moves approximately linear. And this is also the reason why these things just pass through initially, because it's a linear theory near the boundary. But in near the horizon, of course, gravity gets very strong and non-linear. You form your black hole, and you see the spills hitting the boundary. Well, this can be thought of as anisotropy, and everything, well, this whole plasma forms, as I showed you. For these Chesley-Jaffe shocks, it's much duller, because they were so wide already that the spills would be kind of traveling back and forth all the time, and it's all thermalized during this collision. So the intuition is kind of that you have to compare the width with the distance to the horizon, which is kind of 1 over the temperature. And if you then plug in so the idea was always by this gamma factor at rate of 100, it might be very thin, but perhaps not so much.
Can I make a quick comment here about your thin shocks? So in this coordinate system, the shocks, single shock points actually, it moves like this. In some sense, the bulk is the future of the boundary.
Right.
So wouldn't you just expect that bump going up to the boundary just to be a coordinate artifact? Purely based on, the fact that the bulk is the future of the boundary. So the collision's taking place in the bulk before it takes place on the boundary.
So that the collision takes place in the bulk before on the boundary is definitely a coordinate effect. You can also think about it in Verfurman-Graham, and in Verfurman-Graham it would be all at the same time. So this is also why it really takes some time from the horizon to the boundary. It really takes some time. So that will be, that is a gauge invariant thing, so that will be true here too. But on the other hand, we don't think this blob is really a coordinate artifact. I mean, it will arrive also a little bit later. That's why we think the plasma forms a little bit later.
But its motion is just your slicing.
It looks a bit that it arrives at the same time, but it must be a little bit later. And it's also the anisotropy really causes the energy density to change.
But in your movie, it's arriving on the boundary precisely at the time when those things on the boundary start to overlap. Right? So there it is, right there.
No, it should be a little bit later, I would say. Well, in that sense, it's a good question, but well, by this linear argument, I mean, the gravity is really linear near the boundary, so of course it will start at some point to change, but it's hard to say, because I mean, I also argue that in these kind of plots, that the energy density starts at 0 and then starts to grow, but you already see here that it's not really 0, and this is also because these shocks are not infinitely narrow. So I think, by general reasoning, it probably kind of holds, but then we should take them more narrower, have better numerics, and well, I should look and compute the exact number, like what time it arrives. But good. Well, as a second argument why we think we understand this from the bulk is that, so we think we have this dynamics coming from strong gravity deep in the bulk, and then causing this plasma to form, and also the shocks to kind of decrease in height. So here in blue you see kind of the shocks at different times, and you see them decreasing in amplitude, whereas in green I just plotted the shocks at the same time, but just as if they would just move on with the speed of light. And what you then expect, if this comes all the way from the bulk, it needs to, and these shocks travel with the speed of light, this time takes of course longer, so it because there's some extra distance, so this kind of non-linear dynamics has to catch up with the shocks. And you very clearly see this, like for instance in this one, like the front edge of the shock is almost unperturbed, here even more than here, and only at the very end the front edge gets perturbed by this, what we say, this non-linear effect, and I think you can understand this very easily by causality, because it just takes longer time to catch up to this front end. Good, and yeah, then I want to present some new results, which we want to study this a little bit further. And what we then did is, instead of colliding these narrow shocks, we put two of these narrow shocks very close to each other, and another two of these narrow shocks very close to each other, and repeated the analysis. And what is already interesting and perhaps a bit expected, so well, here you see just the same kind of thing. In the middle it looks very similar, and what we also plot here is the apparent horizon, so it's the area of the apparent horizon. You can kind of think about it as an entropy density perhaps, but it's far from equilibrium, so it's not so clear. But anyway, what's interesting is that here we have this microstructure having these two shocks and four peaks, and if you look at horizon dynamics, you don't see anything of that at all. So this whole thing in the IR is washed out. And I think you can understand this because, well, there's a characteristic scale at the horizon 1 over the temperature, and anything which is bigger than smaller than 1 over the temperature cannot be seen at the horizon. And this, because this fluid is kind of, plasma you form is kind of following what the horizon does, you should also expect that this plasma here in the end, which is kind of the horizon, should not be sensitive to this microstructure over there. And that we indeed check. I'll show you in 2 slides. Well, we also checked the second example, where we didn't put them very close to each other, but further apart. And of course, at some points, they're so far apart that you can actually see the difference. And this is in fact the case. So here you see that if you look at the apparent horizon, that indeed there are 4 peaks, but you see still that they're a little bit washed out. But now this is definitely not the same. So this is not. So the plasma is sensitive to this separation because it's big enough. So then I wanted to show you this messy plot. It's kind of messy a little bit on purpose, because there are kind of all kinds of lines, but 5 of these lines in the middle I want you to look at are almost all right on top of each other. 3 of them are not. The one of them is this very broad one. It's kind of well, I'll show you in the next slide. Perhaps I'll show it now. So there are 3 of them. So this is a very broad one. It's kind of this double shock collision, a very wide one, even wider than just the other. Also this very widely separated one, and this rather widely separated one. So they don't lie on this curve. But if you do anything, basically putting 2 of them, changing the width a little bit, so there are 3 of them with different widths, or even, and that's kind of interesting, an asymmetric one, then this middle region doesn't really change, at least if you, so that's what I showed you. And we think that's very interesting, especially also since we checked this asymmetric one, since if you look at, for instance, a proton-lead collision, you have of course a proton hitting like a very big nucleus, but at least in LHC they're really very thin. So we think that if you compare the temperature with the size of this nucleus, that it cannot really resolve, at least if you look at the plasma, the size of this nucleus or the proton. So what you would in the end just get, you would go to the center of mass frame, and the microstructure wouldn't really matter. And you would just get the same thing for this proton-lead collision, and it would in particular be symmetric around the origin in the center of mass frame. So this is a kind of prediction. Then in my last 5 minutes, I'll want to talk a bit about this recent work with Laura Machka and Scott Pratt, where we kind of tried to go a little bit beyond this model by having a collision of also these shock waves. It was at least the idea, but then having a non-trivial transverse profile, a central collision, so it's still axisymmetric. But of course we couldn't really solve this gravitationally, because you could do it, but it's a lot of work. Because you have an extra dimension, so we assume boost invariance in the longitudinal direction. Well, I just told you that boost invariance doesn't really hold, but I have to do something. And what we then did is to do the very first stage is we solved analytically because these boost invariant coordinates, they break down at t equals 0, and you can do a small time expansion of these colliding shocks. And what we then did was if you do a small time expansion, you only know the metric near the boundary. So we had to add an extra parameter to kind of get an initial profile through the whole bulk. And we evolved this using this numerical DR code, which is very similar to the numerical DR code of the shock waves, but then having boost invariance and radial expansion. This is the second part. And then when it was thermalized, we moved on to this region 3, where we used Paul Romatchka's viscous hydro code, which is kind of state-of-the-art, the QCD hydro. And then at a certain temperature, 170 MeV, you freeze out, and you parse it onto a hydronic cascade code. It's called PRET, and this is kind of a state-of-the-art cascade code. And then you can read off your particles, and well, you can see this is compared pions and kaons to Alice, and it's kind of right on top again. So this is kind of proof of principle that you can do this whole matching and pre-flow out of equilibrium using ADS-CFT and get exactly the right spectra, where I have to note that the total multiplicity is fitted. So this is important because we don't really have this collision, so we have to assume this boost invariance. So we have to fit one thing, one parameter. And yeah, if you compare this blue line, for instance, it's just hydro started at 1 femtometer compared to this ADS model, then you see that it does quite a lot better. And yeah, to make this a little bit more convincingly, so we also plotted, like for several of our simulations, the velocity profile at 1 femtometer. So you see the radial velocity, about 50% of the speed of light at the maximum. And it's not very sensitive to all of our parameters, like the starting time from the numerical DR point of view, or this extra parameter I mentioned, at least if you fit this total multiplicity. What we then also, what we studied then is how you go to hydro. So we started these different hydro switching times, and you find out, as you expect, that if you shouldn't start too early. At some point, the restaurant doesn't even exist with its negative energy densities and all that. So then you cannot switch to hydro. You should also not start too late, because in this hydro code, it's really QCD hydro code, so it's not a conformal theory. Although at high temperatures, it's approximately conformal, but so 15% discontinuity we can kind of have by approximating it as conformal. But you shouldn't go too late with ADS, because then you miss out on this non-conformality. Well, and then as a very last slide, I have some prospects, what I'm doing right now. So this is kind of off-center collision, but then assuming that the transverse expansion is much slower than the longitudinal expansion. This makes sense. I mean, the longitudinal time scale is like 0.2 femtometer. The central scale is about 20 femtometer. So what you can then do is, if you can approximate every point as a shockwave collision, and what you get is about something like this. So you can run it, and you can see the energy density and all that. And then, of course, you have to start thinking about doing hydro and freeze out after that, and it's very complicated. That's work in progress. So what I did, as a disclaimer, I put like we're modeling at infinite n, infinite coupling, might not be so good. We're not really colliding heavy ions with a lot of gluons, basically, so it might not be so good too. But on the other hand, I mean, we saw that strong coupling doesn't really give this full stopping, which was kind of excluded by LHC, so this is a good thing. And perhaps we should take this models more seriously. And then for the second paper, I had this pre-flow, which you can produce dynamically and switch. And if you look at these units, you'll find that the temperatures are much higher. So, it might be a bad thing, but on the other hand, it's not very well understood. So perhaps the temperature is much higher, and perhaps then, because one of the temperatures is small, thermalization could be very fast. Well, we saw that this energy density grows initially, funny thing, doesn't happen in other models. And this prediction, which is also, well, in some other models also true, but could be interesting to look at if this proton lab is symmetric in the center of mass frame, which the center of mass frame is a bit non-trivial. And so I already mentioned this Lambda model. Thanks for it. Attention.
So you wrote there speculative. So what that means? What part is speculative?
Yeah, I guess this will never be accepted if you put in these numbers. But I kind of believe in it a little bit myself, but that's why it's speculative. Why it's speculative is also because of disclaimers, so you have good reasons not to believe this. Yes.
can I get you to go back to slide 10?
That was the wrong way, right?
So I don't have a question, but I'm going to make a comment, which is for you and I beating a dead horse. But so here you show the energy density, right? The proper energy density, and clearly it's not boost invariant insofar as it clearly depends upon eta. But there is one striking characteristic of this, and that is that contours of the proper energy density are essentially lines of constant rapidity, which means that the flow, while not globally boost invariant, is locally boost invariant to a fairly high degree of accuracy.
Yeah, so Paul has better and longer simulations, and he think he can say as an argument why this should stay like this for very long times, and yeah, that might be interesting. But yeah, still the statement remains, of course, that it's not, if you boost from 0 rapidity, you want to know the temperature at some rapidity, it's not the same temperature, but you could make use of this fact if this indeed stays constant, which I'm not completely sure of yet. But thanks, man.
Hydro until now had some difficulty in reproducing HBT data from heavy ion collisions. Do you do better here?
And not with this project, Follow-Romatchkin. Yeah, it might be because of the boost invariance. We checked it, and yeah, I don't know more about that. But,
In terms of the spectra, you compared to some, I guess, LHC
yes.
data, and you had this straw man, which was the hydro at 1 femto.
Right.
So I just, since I'm completely outside of this area, is there anything else out there on the market? If you don't, if a theorist doesn't want to use holography, are there other phenomenological models that they could apply to the system that could do better?
Yeah, I think actually, well, so now if you would start at 1 femtometer, you miss out on this 50% speed of light and you're really too late. But if you start a little earlier at 0.2 femtometer, then the error is not so big by not having this. I mean, the only thing what really matters is the energy density, which is kind of just the energy density of a nucleus, and the velocity. That's your only input for hydro. So if you just start at 1 femtometer with 0 velocity, you miss out on a lot. So that's pretty bad. If you start at 0.1 femtometer, it's not so bad. So that could be a good thing. Or you can try to cook up a formula which kind of reproduces this curve by.
What about models that aren't hydro? I mean, that we want to.
So they try to have they have these Glasma models, and I think they do fairly well too. Yeah. Yeah, they kind of reproduce this kind of curve, and then they can do the same thing.
Okay, so I don't see any further questions. So let's thank you.